So shall we start?
Yeah, I think can we wait for 1 more minute or so?
Yeah, okay. Okay.
Ramaya garu, are you able to hear properly? Ramaya garu, మీ వైపు నుంచి నాయిస్ వస్తుంది బాగా. No, your mic is noisy. It's okay. I think we can begin, Srija, now.
Yeah, okay, okay, sir. So good evening, everyone. So welcome you all for the fifth day of this program. Okay, successfully we have come for the fifth day of this program. So today we have the coordinator of this program, Professor P. Vishwanath, Associate Professor in IIIT Sri City, as our first expert. Let me give a brief intro about him. So Dr. Vishwanath did his BTech from SV University, Tirupati, MTech from IIT Madras, and PhD from IIC Bangalore. He worked as a faculty member at IIT Guwahati for about 4 years. Currently, he is working as an associate professor in IIIT Sri City, and he has authored nearly 100 papers in both journals and conferences, and he has guided nearly 7 PhD students towards their successful PhD completion. We welcome you, sir. Over to you now.
Yeah, good evening. Yeah, thank you. So let me share my screen. So my screen is coming up.
Yes.
Yes, sir.
So you are able to see the screen, I think, and you are there is no problem with the voice.
Yes, 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 sir.
So let us begin this one. So this is introduction to ML. So let us introduce AI and ML because ML is part of AI. So let us see about AI also. So this is the expected triplet toxicity. Right now, triplet toxicity is 1/4 of this one. So when it comes to artificial intelligence, it almost like there are two separate branches are there. One is so-called traditional AI, other one is the modern machine learning. So the traditional AI is what is called as rule-based or symbolic, and modern AI is what normally is called as sub-symbolic. Okay. So when AI has been started, it was under the learning paradigm, which is called as deductive learning. We will see what that is. So there is something else also, which is called as inductive learning. Okay. So today's machine learning is inductive learning, but previously AI, which was rule-based or symbolic-based, was a deductive learning. So artificial intelligence itself was first coined in 1956 at a conference. So this is one of the biggest things for us, artificial intelligence in the civilization. This is affecting our civilization itself. So there are various definitions for artificial intelligence. This is one of the definitions. So what this is saying is that what human beings are able to do, if the machine can do it, means then the machine can be treated as intelligent. This is what after all these definitions are saying. So by the way, if you have any questions, you can raise in between also. You can unmute yourself and you can ask your question. So in AI, these are all the AI is an interdisciplinary subject. So where many disciplines have contributed, one can see that there are so many things that have been contributed, and this circle can be seen as topics of AI. Something outside is also there. For example, image processing is generally considered not part of AI. Speech recognition, some portion of that one is part of AI. Okay. Whereas graphics is not considered as AI. Robot control, some portion is considered as AI. So, like this, one can draw a Venn diagram kind of thing to see that where it is cutting with the disciplines or some other disciplines, so on. So, what we have already achieved in AI? In AI, if you see board games, we are able to do relatively well board games, chess, checkers, all these things. Nowadays we are having machines playing better than human beings. And also we are having Google Maps, which is guiding us in driving. Also we are having image recognition, speech recognition, where nowadays that what do you call that hands-free way of handling a mobile is also there, so that only with speech you can make a call and you can do all the controls of the mobile phone or by using the speech, right? And also nowadays we are having a fingerprint recognition, face recognition. All these things are already existing in our time itself. So today's AI is more or less like this. So we are having almost these symbolic things we achieved. The board games, all these things we achieved. So something like a handwriting recognition, like OCR, we have achieved reasonably well. Understanding speech, images also we achieved reasonably well. There is Siri which is working very well. Similarly, the diagnosis in the medical domain, we reasonably achieved this one also. As with human beings intervention, the machines can help the doctor in doing the better diagnosis. Also in the computational geometry, machine learning has helped a lot. And what is going to happen in the future? This was a survey conducted at some conference, some old survey this one is. They are saying that writing a best-selling book, AI will be able to achieve by 2049. Working as a surgeon, completely automated surgeon, we will be achieving it by 2053. So outperform humans in all tasks, 50% chance within 45 years. Within 120 years from now, maybe everything can be automated. So this is going to happen actually. It's not a fiction. This is going to happen. We are already seeing translation of languages. This is already achieved, right? And programs now, NLP programs are there which are capable of writing high school essays. This also is already achieved actually. Driving cars is more or less achieved, but driving a truck is a big thing. That will be achieved in a couple of years, right? So it is not something which is done only for academic purpose and then only for in some areas only it is. No, this AI is going to affect our civilization. Our civilization itself is going to take a turn because of this artificial intelligence. So what are the techniques that are available in artificial intelligence? There are deductive and inductive, as I told already. The deductive is a traditional one, which is rule-based or games, something like that. So that means it is hard-coded. And the thing is here is that we know how to achieve something. This is, we already have the knowledge. We already have the knowledge. For example, how to play chess, we already have that knowledge. Only thing is that we have to encode it properly, and then we have to take the help of a machine to in an exploration of the next step. What is the better step in doing that one? Okay, this is almost like when we are using machines to do multiplication, we can give an algorithm which is going to multiply two numbers, right? So we are going to give step-by-step procedure. so that it is going to do the multiplication. Similar to this one, step-by-step procedure we are going to give so that it is going to play the chess game. So there is nothing more, nothing less here. Deductive learning means it is the rules of the game are pre-given, pre-encoded. Okay. So we know what we want to do and we know how to encode it. So we are going to write our programs. We use our algorithmic knowledge. We will achieve the task. Inductive learning means we don't know how the task is achieved. For example, when it comes to driving a car, exactly how human beings are capable of driving a car, we don't know this. Or exactly how human beings are able to recognize voice of a person. We don't know this. Exactly what is happening within the brain, we don't know this. Right? It is not like doing multiplication of numbers or something like that. But what we have is some examples are there. Some speech signal saying that this is speech signal for hello, this is a speech signal for some other word, so on. We are having some examples are there, labeled examples, we say that. Apart from that, we don't have much knowledge. We are having data here. Perhaps along with their labels and all these things, we are having data. We want to learn how human being is able to do this task. For example, how a human being is able to recognize voice. We want to achieve that one. So here only examples can be collected. And from the examples, now we want the machine to learn on its own. So this is almost opposite to what is called as deductive, where we give the knowledge. Inductive is we don't give the knowledge, but we give the examples. We give only the data. From the data, knowledge has to be learned by the machine itself. That's why machine learning nowadays is a separate field. Even though it is normally said to be part of AI, machine learning is a big part of AI actually. And some people argue that machine learning is a separate thing. It should not be seen as a subset of AI. Some people argue like that. But nevertheless, once we see everything as learning either from the pre-given rules or learning from examples, both are learning only. So the board games, we know that how the board may be represented and how the two players can be represented, how the state space can be explored, how a game like tic-tac-toe can be played. Maybe most of you might be knowing this one. This is a game tree where game tree can be explored. It can be explored and one can give some goodness of a board position. Some goodness can be given to each board position, how good you are. And based on that, one can choose what is the best step, next best step. So the machine is going to play like this. So that's why this is a known thing for us. That is, we have hard coded this knowledge of goodness, knowledge of the next move. All these things are hard coded into the machine. That's why it is called as deductive learning. Are you having any questions?
No, sir.
Right. When it comes to rules for self-driving car, you can't give rules. You can't give a rule like saying that when a pedestrian is there, slow down. And the machine will not understand that. What do you mean by pedestrian? What do you mean by he is there? What do you mean by slow down? Machine will not understand these things, right? So self-driving car, you can't hard code like this, just like playing a board game where a board position can be represented with a 2D array, like a matrix, right? But here, how you are going to represent the road, how you are going to represent a human being, all these things is a mysterious thing for us actually. How a machine can be capable of driving a car is the most mysterious thing, right? So giving uh, rules for this attempt is going to fail, and it has failed actually. It's not possible for us to give the rules, but we can give examples. We can give examples saying that this is a good driving pattern, this is a bad driving pattern. So the machine has to learn a good driving pattern, and in the training we say that there is a training set is there where the human being will be driving, and all the sensing things will be taken, and what are the human actions based on the environment, it is recorded as a sequence. So this forms an example. So like this, there are so many examples are there. From these examples, what do you mean by a good driving has to be learned by the system, right? So it can learn rules from the data. So these rules, it's going to learn from the data itself. So for machine learning, data is very important. And from the data, one has to learn. So this learning is what we are calling as machine learning. These algorithms are machine learning algorithms. This data is called what we generated, what we sensed, or what we generated, or what we collected is the data. For example, students' marks we are going to store. So this is the data, right? Now, this machine learning algorithm automatically is going to work with this data, is going to extract the rules or something like that. And finally, it is going to do the business, whatever is our machine learning business. Like it has to recognize that there is a pedestrian is there. So given a video frame or video scene, the machine will say that there is a pedestrian. Yes, there is a pedestrian is there at this much of distance he is there. So something like that, this is going to learn. So this is going to happen. There should be, we require something called as data is needed for this. This is what is called as examples also. Examples is same thing as data. So maybe there are positive examples, negative examples saying these are good way of driving, this is bad way of driving. So all these things are there. Those things can be called as labels. We can label the data element as its goodness value or as its label, right? So this is typically what is called as the training set. We want to train the machine with these examples, and we want the machine to do whatever human beings are doing. So the learning is done by machine learning algorithm. So let us go to the next step. So now machine learning, if you are interested, this is a very fascinating field, machine learning. If you want to become an expert in machine learning, there is nothing mysterious in machine learning. After all, it is going to depend on these things: probability theory, linear algebra, calculus, algorithms, data structures, and some programming skills like Python programming or something like that. With these things, with some mathematical and with some computer science background, anybody can become an expert in machine learning. It's not a rocket science. Uh, Even rocket science, anybody can learn, right? When it comes to strategies, there are various paradigms are there, machine learning paradigms, like supervised machine learning is there, unsupervised machine learning is there, reinforced machine learning is there, so on. So in this one, we will see about supervised mainly, and maybe we will touch upon unsupervised. And the next speaker will touch upon unsupervised in a much more deeper way, right? And there is something called as learning what is good attributes. So we'll go into that supervised learning now. Now, this is the example. First example I want to give is that we see this example, we have shown to a child a set of dog pictures. We say that these are all dogs. We say that these are all cats. We show it to the child. Okay, the child has seen these pictures. Okay, and then we will ask the child, what is this? If the child is able to say that it is dog, then the child has learned. And one has to understand that this picture as such is not in the training set. In the training set, whatever we have seen in the previous slide, that picture of dog was not there here. So that picture is a new one, which is not in the given training set. Even then, the child is able to say that this is a dog. That means the child has understood something which is common among dogs, something which is common among cats, and hence the child has learned the pattern, the regularity behind all dogs, the pattern behind all cats. Right. So that's why some people like to call this field as pattern recognition. Both these pattern recognition machine learning are same. Some people, this is the old name actually. Pattern recognition is old name. Machine learning is the new name. So how actually this is done? Mathematically, finally it has to be represented. Symbolically, one has to represent it, and then one has to work with that one, right? So here comes something like a vector spaces. Okay. So object, a person. Maybe you will say that X is a person. Now for a machine, what do you mean by a person? For a machine, the person means some numbers, some attributes, or some values given. Maybe height, weight, color. Maybe there are three. There are dots are there here. Height, weight, color may be there, which is a categorical attribute. Also his blood sugar level or heartbeat level. All these things may be a big vector of numbers along with categorical attributes. Like what is his skin color, what is his hair color, all these things also can be coded as a big vector of these values. So this vector of values can be seen as a representation of the human being. This is what we mean by the representation. We can work only with the representation. We don't know what is it mean to work with a human being. We can only work with a representation. This representation normally for us is going to be a vector of values, feature values. So each one we say that is a feature value. It may be a number, it may be a categorical value, it may be an ordinal value, whatever is that. We say that this is going to represent the real world object. So each of these objects in the real world, for example, cat 1 is represented like this, cat 2 is represented, cat 3 is represented. So all these things put together is what is called as the feature space. The feature space is, we denote like this, feature space. So the set of all cats, all dogs. For example, if we are interested only in classification between cats and dogs, the set of all cats and all dogs is what is the feature space. Okay. Now the important thing is that what should be these attributes. Okay. Some people will say that weight, height, color, all these things may be possible attributes. Some people will argue that no, it can't be. There should be some low-level attributes should be there. We should do some image processing and we have to employ a filter here. And what is the value of the filter when it is filtered with that filter? What is the value we are going to get? That should be one attribute. The other filters value should be the other attribute. Some people will argue like this, right? Nevertheless, these are only the representation of the real world object. So there is a label for the real world object. For example, here cat is a label, dog is a label. So like that, there are labels are there. So that's why we say that the feature space is the set of patterns, basically these vectors, set of vectors. These are the labels given to these vectors. Some vectors we are having labels. So from some vectors with labels, which is called as the training set. Some vectors are there with labels, which is called as the training set. From that training set, This is also called as the example set. We want to learn the mapping between every vector to the label space. So this is the attribute space. This is the label space. Given the vector here, whatever vector I am going to give, I want to tell whether it is a cat or dog. So before this, how this vector of values is obtained is not our concern. Actually, some low-level people like ECE people or sensor people or physics people will be doing that one, how to collect these attribute values. Machine learning person is interested in finding this mapping between this one. Given the vector of values, how is that if I give this as input, I want to get this one as the output. This is what is called as classifier learning. This is exactly what is called as the classifier learning. Okay, for example, here for a person, maybe we are going to represent the person using height and weight only. We are not interested on many other things. And we want to classify the person as overweight or normal. That's all. These are the only two labels. Because this is the problem we are having. So given height and weight, we want to classify as overweight or normal. Maybe this is an easy task. Given any height and weight, we can do this one. Maybe it can be done in a deductive way also or in an inductive way also. So this is the traditional machine learning techniques are like this, where actually we are sensing, human beings are also sensing with eyes and ears. There will be some pre-processing to get the attributes or features. Features are extracted, feature vector is there. Then comes the machine learning into picture. The machine learning is going to create the classifier, which is the function f is created here. This is going to take the input as the vector. The vector is given as the input here. And this is going to give the label, class label. So this is what the machine learning broadly is. Okay. Do you have any questions? Shall we go ahead? Yeah.
No, sir.
We'll go ahead. Now features, sometimes some features are good features, some features are bad features. For example, if you want to classify between height, overweight and normal person, height and weight are important features. Whereas glucose level or other parameters, medical parameters may not be of important. Height and weight are the important features in order to classify a person as overweight or normal person, right? So selecting good features from the given set of features is one of the important tasks. Okay, so this is called as feature extraction or attribute extraction. This is also part of machine learning, and this part as such is traditionally done by ECE people or electrical engineering people or physics people. They will do this thing. Okay, right. But nowadays there is some shift is there. We will see that one. Okay, so features has to be extracted. So we require sensing devices, sensors are needed, and we should know it can sense so many things, but what are the good things for the given problem? One has to find out these are the good attributes for this problem. So we can work only with these attributes. One has to say that one. So this can be done. And nowadays there is a slight paradigm shift is there. We will see that one. So when it comes to overweight and underweight, this is the feature space. So we are having examples. The training examples are like this. One can see that these are all overweight persons. These are all normal persons. This is the training set. Now, given anything in this space, given any point in this space, having any point means it's going to have height and weight. We have to say that height and weight, is it overweight or underweight? Okay. So actually here the domain of this problem is not all heights and weights. Negative height, negative weight will not be there. The domain of this one may be something like is going to be maybe starting from this point of height, starting from this point of weight, only above this is going to be there. not all points. Anything above this, anything above this. If we give a point, we want to classify it as normal or overfit. Okay. So feature extraction has to be done, good features has to be learned, and then we create the training set where the vectors are created, the labels are given. We are going to build a classifier by employing some machine learning algorithm. Right. So this slide is maybe important for you. This is what traditionally machine learning was like this. Traditionally, it was like this. The input, the sensor input is given, features are extracted. This is the vector. The vector of features are there. It is given to the machine learning algorithm. Is going to find the function. This is the function actually. How the
Sir,
mapping? Yeah.
there is a question from Mr. Sanjay.
Okay. Okay.
Yeah, he has.
Sir,
Hmm.
sir, exhaustive domain is required for training set, sir.
Mathematically, yes.
Okay, sir.
Theoretically, yes. But practically, exhaustive domain, we never will be having exhaustive domain.
Okay, sir. Okay, sir. Thank you.
There is a gap between theory and
Yes, sir.
practice.
Yes, yes.
Okay. Okay, let us come back to this one. So this is what traditionally being done. So maybe up to this part, ECE people will be doing. And after this, CSE will be doing, as well as ECE also can do. But this part as such, the lower level part, is traditionally, it was done by electrical and electronics people or physics people. But nowadays, this is called as the deep learning era. In the deep learning era, which has begun in 2012 or so, 2012 may be said as the beginning point, or 2010 may be said as the beginning point of this era. In this era, this division is not there. This division is removed actually. Now we are saying that this entire thing is a single thing. This single machine learning algorithm has to learn from the given sensed input, that is the raw sensed input, like image. We are going to give only image here. It has to learn what are the good features, and then it has to learn what is that function f, and then finally it has to give the label as cat or dog. So we don't do anything manually here like done in olden days. So this is what deep learning era is. And this is successful because of some factors. This deep learning is very successful. We'll see that one as we go ahead. We'll see why deep learning is so successful, why people are talking about deep learning nowadays so much. We'll see about that one as we are going. But the main difference between traditional machine learning and deep learning is this one. The classification problem, we know this one. Given a training set, we want to build a classifier. And once we are going to build a classifier, so building a classifier means learning this function f, which is going to classify for the given x, it is going to give the label y. We are trying to learn this function f, right? One has to evaluate how good is this f learned f, right? One has to quantify how much good is your classifier. So for the training set, if it is 100% correct with the training set, is it okay with us? The question is that if it is doing 100% with the training set, so training set is there, like this is the vector, this is the label, this is the vector, this is the label, this is the vector, this is the label, like this. Training set is there. And I learned a function f, which is going to do 100% correctly with the training set. Is this what I want? But the answer is that no, this is not what I want. If this is what I want, then I can remember this one. I can store this one in a table, and then whenever this is given, I can retrieve this one and give it. But this is not what I want. I want what is the pattern behind all these things. I want to find that regularity behind all these things and the relation between this feature space and the label space. This relation at abstract level, I want to, okay. Something which is not in the training set has to be classified correctly. So that is the test. The test is that how to evaluate a classifier is that something which is not there in the training set has to be classified correctly. Then the classifier is a good one. Okay. Remembering training set as it is and then working is not called as learning. Nevertheless, this is also having a name. This is what is called as rote learning. This is what some people might be doing, remembering by hearting. This is what is called as by hearting the question answer things. Whenever the same question is asked, the answer is given. If a new question is asked, the person don't know how to answer it. Okay. So the students studying in some private or some coaching centers, there may be guides, big guides are there. Questions, answers are given. So they are trained, given this question, write this answer, given this question, write this answer, like that. But this is not learning. This is called as rote learning. The machine, we don't want the machine to do this rote learning, which is remembering the training set. We want it to generalize from the training set. So the learning techniques, the algorithms we are having to learn from the training set, the classifier, there are so many things are there. Base classifier can be learned. Hidden Markovian models are there. Nowadays, artificial neural networks are there. Traditionally, decision trees was there, and now also it is there. It's a good one. Decision trees, support vector machines are there. There are many other learning algorithms are there. Nowadays, it is deep learning era, so we can say that one big bullet will come here. Convolutional neural networks is going to come here. Maybe tomorrow some other technique is going to come here. Okay. And this is one more taxonomy of the learning methods. There are generative methods which tries to understand how the feature vector can be generated. Given the training set, how a feature vector can be generated. So that means it tries to understand about the distribution. Discriminative is it doesn't care about how to generate, but it wants to discriminate between the classes. Given that this training vector is for a cat, this training vector is for a dog, how is that I am going to discriminate between these two things? That's all. We don't want to generate a cat image. We are not interested in generating a dog image, but we are interested only in classifying or discriminating between cats and dogs. Okay. So one good example for this one is that if you want to generate a chair, you require all the material are needed, you have to generate a chair, means, right? But if you want to discriminate between chair and table, then the easy answer is that between chair and table, because chair has 4 legs, table has 4 legs, chair has a flat surface is there, table also has a flat surface, but the armrest or the rest for the backrest is there only for the chair. So one can say that this backrest, armrest are the discriminating features between chairs and tables. So if you want to discriminate between chairs and tables, this information is enough. But this information is not enough if you want to create a chair. If you want to create an image of a chair, this information is not enough. So there is a difference between this and this way, right? So the algorithms can be doing either this way or this way. There are many techniques explored either this way, many techniques explored in this way also. Now there is a classifier called as k nearest neighbor classifier. So this is the given training set is like this. You can see that the training set, there are blue classes there, blue circle class is there, and white square class is there. And we are asked to classify this red point. So which class it belongs? Is there any answer? Blue class or white class? You may type in the chat box. blue. Obviously, many people will say it belongs to the blue class because it is very close. It is within the blue cloud actually. Blue points are surrounding, so it belongs to the blue class. The k-nearest classifier, what it will do is that it will see what is the first neighbor for this one. Nearest neighbor for this one is this. But if it is going to rely on only the one neighbor, it is going to say that the class label is this. This is wrong. This is a wrong answer actually, right? Classifier can go wrong. If it is going to rely only on the first neighbor, thinking that whatever in the training set which is very close is going to give me the label, then it may go wrong because there can be noise, there can be outliers in the training set, all these things. But if we increase the number of neighbors we are looking at, for example, if I am going to look at 3 neighbors, let us say that I am going to see these 3 neighbors here. If I take the 3 neighbors, then 2 are blue, 1 is white. So I will say that it is blue. Okay, so this is a classifier. Nevertheless, this is called as the k-nearest neighbor classifier. It will store the training set. There should be a distance so that for the given example to be classified, marked with red here, given example to be classified, we will set with the distance metric, we are going to set what are the k neighbors for this one. Based on k neighbors, we take the majority vote. We are going to assign the label for this one, the majority vote label from the training set. This is not rote learning. This is a valid, legitimate machine learning classifier. Okay. Then the other type of classifiers are like this, which is going to learn the discriminant. That is, it is going to learn a function. This function is almost like a mathematical formula. This function, like this is a function. Given x1, x2 feature vector to this function, this is going to give the label. Label, maybe we will say that class 1, class 2, something like that. So maybe here we represented this function f like this. So this function f in the feature space is going to be this line. This line we know that can be represented with this equation. So on this side, maybe we can say that this is the positive side, this is the negative side, because the point on this line is going to be equal to 0 here. On this side is going to be positive, on this side is going to be negative. So whenever I give x1 and x2, I will apply this formula, and if I get a positive quantity here, I will say class 2. If I get a negative quantity here, I will say class 1. This is typically how the discriminant based classifier is going to work. Okay. So this is what is traditionally called as perceptron also. Perceptron name, many of you might have listened or heard perceptron. Perceptron is nothing but this linear discriminant classifier. What we have seen is called as perceptron. This was one of the first classifiers which was created in 1960s. Okay, and that may be said to be the birth of the neural networks. Okay. When it comes to the linear classifier perceptrons, all these are doing very extremely good with the training set. But the last one, that is the black one, is a better one. How can you say that the last one is a better one? Is that one can say that now if this is the classifier, the discriminant learned by the classifier is this one. One can tell the goodness of this one by quantifying how far you can go away from this, so that you are going to touch either positive example or negative example. So this can be quantified as the width, margin width, and that discriminant having maximum margin is a better one. So here this is a better one, right? So this is what SVM will do. That's all. This is what support vector machines are doing. It is a linear. It has started like that, linear, with maximum margin. Linear discriminants are called as support vector machines. Then non-linear support vector machines also came into picture. And then neural networks came into picture. Neural networks came into picture before support vector machines, and now also it is there. So neural networks, it will try to say that it will try to find a hidden representation. This is the given representation is this one. This is the feature vector X is this one. And we will try to find some hidden representation, and from that one we are going to get the output. The output finally we are going to get. So these are connected here with the weights. So with the weights, so these weights are there here. We do some operations with, because this number is there, number is multiplied with this weight. We are going to add up all these things. We are going to employ something called as activation function here. Okay, some activation function is going to give the output. So this is like a threshold function. This is how basically a neuron is going to work. Human brain neuron basically might be working like this. It is getting input from various sensors or from the nearby neurons. And if this activation is over some threshold, it is going to fire. Okay. So from this one, they said that they created a mathematical model, something like this, and they created a classifier learning technique, which is called as artificial neural networks. So we do have a well-established field now, which is called as artificial neural networks, where training methods are there using backpropagation technique, all these things, right? In the deep learning era, deep learning is nothing but it is a neural network only, but with several hidden layers. The number of hidden layers can be in tens or in hundreds. So that is what is called as deep learning. Okay. Generative models are there. Similarly, normally what we do is that we assume something about the distribution from which the data is coming, and then we will try to estimate the parameters of the distribution. For example, if the distribution is normal distribution, if we are going to assume that it is coming from a normal, which is also called as Gaussian, then the parameters are mu and sigma square. If we can estimate this mu and sigma square properly, then we can generate also the data we can generate. We can use this information to classify also. We can use this information to generate examples also, right? And inherently, there is no better classifier. We can't say that this is the best classifier learning algorithm. There's nothing like that. Based on the domain, some classifiers may be doing well, some classifiers may be not doing well. So there is something called as no free lunch theorem, which says that there's nothing like the best classifier. Okay. And then when it comes to evaluating a classifier, there are two components, bias and variance. Bias is from the ground truth, how much it is deviating. Ground truth, it is deviating, how much it is deviating. And variance means it is going to oscillate here. It's not going to deviate from fixed quantity, it's going to oscillate. Because the randomness is going to come into picture, it's going to oscillate. So this is the bias is this one. How much it is deviating from the ground truth on average. Variance is the variance of the output. Output need not be the same output always, right? Output can vary because the training set is generated from a distribution basically. So that's why the label predicted, there should be a variance in the label predicted. It's not that deterministic variable is going to come into picture, right? Even for a self-driving car, pedestrian is there with a probability 0.9. That means it's not a pedestrian, maybe it is a pole. With probability 0.2, it is a pole. Right. So there is going to be bias and variance. These are the techniques to measure the goodness of a classifier. Finally, something which is not in the training set has to be classified correctly, right? And there are bias variance analysis is there. Underfitting is a problem where the classifier is not learning at all. Overfitting is also a problem where the classifier is too much complicated. It is doing extremely well with the training set, but not so well with the test set. That's called as overfit. Overfitting has to be avoided, right? Maybe because the time is over now. The next one is the features. The principal component analysis I want to explain how the principal component analysis can be used in face recognition. The features, these are the features. What are the good features to represent? Sometimes if you want to represent the image, the entire image, you require 1 megapixel, right? That means 1 million pixel values are needed. Do we require 1 million values to represent one face? That's the big question that is asked, right? People say that no, maybe some 10 or 20 values should be able to represent a face. What are those 10 or 20 values? Principal component analysis is the feature extraction technique is going to tell us what are those 10 or 20 values. And then unsupervised is called as a clustering. The next speaker may be speaking about this clustering techniques. So if you have any questions.
Good evening, sir.
Good evening, yes.
Sir, actually, you said after 2012, this is a deep learning era. When we have a text or something based on the input, if it is images, then only we will go for deep learning. Otherwise, based on the input, we need to decide that.
No, the raw data means nowadays is the vision-based data is image, video, or audio data is there. Our text also is raw only.
Text.
The typed text or handwritten text, it is also raw data only. There are different type of techniques are there for processing the sequence of typed letters or something like that. Text processing is called as natural language processing. That is also comes under deep learning. So for that also nowadays, earlier it was done traditionally, feature extraction and then going for a classifier. Nowadays, automatically the features are learned.
Okay.
Even for text data, automatically features are learned.
Okay.
Sir, one question. How to decide whether we should go with the classical machine learning method or deep learning method?
Based on the amount of data we are having, based on what data we are having, how much data we are having, what is our processing power we are having. If we are having huge amount of training data, many cat images, many dog images are there. Let us say that 1 million dog images, 1 million cat images are there, very good images are there, then one can go for deep learning. But if we are having hardly some 20 cat images, 20 dog images, then support vector machine may be good. Neural network may not do that much better. Support vector machine can do better. So depending on the situation, one has to see which one is going to do well.
Thank you, sir.
Sir, how this automation is done in deep learning for the feature extraction?
Oh, this is a very good question actually. This is $1 million question. How it is done? That is the soul, that is the heart of deep learning. This is what you are asking. That takes perhaps an hour to explain. Basically what happens is that filters are created. If we are processing an image, basically images are video or audio, the filtering is done. These filters are automatically created. That's what deep learning is doing. But if you want to fully understand this, it will take 1 month time for you. If not 1 month, maybe a few hours it's going to take.
Okay, sir. Thank you.
Any other question? See, deep learning is nowadays a big era, actually, big thing. Many people are working with deep learning, and Python is having so many libraries are there, toolboxes are there, and so many data sets are available. One can even do plug and play kind of thing, and one can almost randomly invent some new thing also. One can write a paper easily, but one should know the vocabulary used in deep learning, and one should know how to use Python with these toolboxes. Hardly some 50-line code can be a good classifier. That's all. A 50-line code in Python may be doing the neural network classifier. So that's why nowadays many people are working in deep learning. That is because of Python language, because of the machines available nowadays, because the machines are cheap. Even in laptop, one can run something, but the processing power is required. People are buying something called GPUs nowadays, graphical processing units. Okay, so that the processing can be done in a faster way. With all these things, the deep learning, the machine learning is growing like anything. There are many PhDs produced every year in this area, and it is quite easy actually to work in this area, provided you have energy, passion, and the drive to do something. One can always do a new thing here. Okay. So with this last remark, I would like to thank all of you. Thank you very much.
Thank you.
Yeah, thank you, sir. Thank you for the wonderful session. Okay,
Thank you,
you
sir.
just gave the clear difference between AI and MI, and how like MI have evolved. Okay, these years. It was a very nice okay talk. Thank you, sir. Thank you very much. So
Thank you.
let's take a break for 2 minutes. Okay, around 8 we will start again. So the next speaker is with us. So around 8 we will start again. Good evening, Professor Vidyut. Shall we start?
Yes, madam. Good evening.
Yeah, good evening.
Good evening,
Yeah,
madam. Good evening, sir. Professor Vishwanath.
yeah, good evening,
Good
sir.
evening, Professor Vijit. Good evening.
Yeah, let me give a brief intro about yourself and then you can start, sir. So, okay, we have our second speaker with us, Dr. Vidyut Kumar Patra. So, he has received his BTech in CSE and MTech in CSE degrees from University of Calcutta, and he earned his PhD degree in computer science engineering from IIT Guwahati in 2012. He was awarded the prestigious Marie Curie Fellowship by the European Research Consortium for Informatics and Mathematics, France, for conducting independent research at BTT Technical Research Center of Finland. Presently, he is an associate professor at IIT BHU Varanasi. Before joining IIT BHU, he was faculty member in the Department of CSE, NIT Rourkela. He has published research articles in high impact journals such as Knowledge and Information Systems, Knowledge Based Systems, Pattern Recognitions, Expert Systems with Applications. And he has been recognized at ECIR and COTS Comet. He completed a few sponsored research projects and supervised a couple of PhD students as well. His research interest includes data mining, machine learning, and recommender systems. Thank you, sir. Thank you for joining this event. Over to you now.
Thank you, madam, for nice introduction. This is really my privilege to be associated with IIT City. So thank you to Sir Vishwanath and Madam you. Let me share the screen. I'll be off, means video, I'll make it off. Hopefully that screen is visible to you.
Yes, sir. Yes.
Yeah. So I'll be talking about decision tree and then base classifier in today's talk here. So outline will be introduction to classification. I think Sir has already covered this part. So just I will take 1-2 minutes. Then I'll be talking about decision tree. At the end, I'll be talking about Bayesian classifier. So the formal definition of classification, the task of classification is to assign an object into one of the predefined categories. That means we'll have a set of categories, and then if the new objects come, that means the object which belongs to test set, that objects basically we need to find the class level. So more formally, that is given a data set of objects and the classes. So task of the classification is to find a mapping, find a relationship between the object and category so that each object is assigned to any one of the class. So more formally, that is a class is nothing but a subset of the classes that contain precisely those objects that map to the class. So it will be much more clear in the next slide, hopefully. So working principle of classification is as follows. So we should have a set of objects with their categories known. So that is something called, we say, the training set. And then we should make a model. So model is nothing but it will find a relationship between the objects and their category. And then final task is to, for unknown object, we need to find the category. So this is more like we have a training data set where X is an object and YI is the class level. And then we classifier will make a model, and that model will basically identify the class level of the unknown object. As you can see that XK is an object where we don't know the class level, whereas here XI is also an object, but we know the class level. So this is the task of the classification. So in classification can be done. So in many ways, there are many examples of classification, that is predicting tumor cell as cancerous or non-cancerous, categorize the new articles into one of the predefined categories. As I said few minutes before, that one has to know that categories beforehand. That is, in this example, that is political news, sports news, entertainment news are the predefined categories. And then any news article comes that should be classified into any one of the this predefined categories. There are many more examples, categorizing animals as mammals, non-mammals, classifying email into spam, non-spam, identifying credit card transaction as legitimate or fraudulent. So these are the example of the classification task. So there are many classification methods, sir already told in that line, that is decision tree, Bayesian theorem, support vector machine, neighborhood based classifier, neural network, and the ensemble classifier also. So this is one example of the decision tree. As you can see that few minutes before I said that any decision tree is a classifier, so it should have a training data set. That table 1 shows the training data set. So basically here each row is nothing but an object. So here, and then class level is yes or no, whether that guy is cheat or not. So this is basically a bank data set where each object is described whether that guy has refunded the loan or not, what is the marital status, and what was the income, and then finally whether that guy was cheat or not. So these are the classification. This is the training data set, and out of this training data set, a classifier or a model is built. So that model is here. Example is the decision tree. We'll be seeing how this tree is built, but we assume that out of this training data set, this model is built. And now what is the task of the classification? Just few minutes before I said task of the classification is to identify the class level. So we had the training data set, now we have the model, and now task is to identify the class level. So now the unknown object which is not there in the training data set, we need to identify the class level. And that guy is refund, yes, no, he did not refund, and the status was single and income was 81K. So we need to find the class level using decision tree model. So model is here. So we need to identify the class level. So how it works basically. So we need to trace this tree. So first attribute is refund. So then we'll trace it refund. So it is no. So then we'll move on the right side, and then we see the marital status. So that given case is single, and so therefore we move on the left side, and then income is 81K. So income has also two branches. So the left side is less than 80K and right side is more than 80K. So therefore we should move it here, and then this is something the yes, that means actually that class level is yes. Just to introduce here, so these are the leaf node which basically indicate the class level, and the internal node basically indicate the attributes apart from the class category attributes. Okay, and then we'll see more details in the next part. So here decision tree is very popular. About something good about the decision tree, it is very popular classification method, and interestingly this model is interpretable. So many times that deep learning is doing very good everything, but it is not interpretable. It is very difficult to understand actually that how it is doing so good. So if someone does not know the mathematics, it's very well. But in this case, this model is decision tree is very easy to interpret it, and then this is very simple for model building, and prediction accuracy is not really bad, and prediction progress is very straightforward. And interestingly, another is it can handle nominal, ordinal, and continuous attributes. So in some scenario, so some classification algorithm, it may not handle the all type of data, but decision tree can. So formal definition of the decision tree, here we go. That is, decision tree is a classifier. A decision tree corresponding to a given training set. As I said, the classifier should have a training set. For a given training set, one can build many decision tree. So a decision tree correspond to a given training set has the following properties. What is that? As I said, each internal node denotes the test condition on the attributes. I said the attributes, so little more that it should identify some test condition on the attributes. And second is each branch represent an outcome of the test. and each lib node has a class level. So if we move back in the previous slide here, now we can explain. So as I said that each internal node is the test condition over the attributes. So test condition here, whether income is less than 80K or above 80K. So that, and it has the two outcome. It can be more than two outcome, but in this example we have two outcome. And internal, that is leaf node is leaf node is basically it indicates the class level here. And yeah, each leaf node holds a class level. Each branch represents an outcome, and then internal node has the test condition on the attributes. So now actually how the tree is built. So how the tree is built, that is the Hans algorithm we use. So that is let Tn be a training set associated with a node n. If all record in the training set belongs to a single class, then node n is the leaf node and labeled as the class C1 and no need to do anything. If all patterns or all objects belong to a single class, so we will end that algorithm there. Otherwise, if Tn records, that is the number of records in the training data set, belongs to more than one class, then we need to identify one attribute with the test condition that partition the records into some smaller subset, and then we apply the recursively this procedure. That means we'll see in the next. That means first condition is like if the all records belong to a single class, then we are done. If it is not the case, that obviously the training data set all records should not be in the must not be in the same class. So therefore we should follow the second step. So we need to find a test condition so that we can split the record. We can partition the record into smaller subset. So let's see this training data set. We have the training data set in the table. As we can see, we have 10 records, and 10 records, all record, they do not belong into the same class because there are two classes. Few records in this example, 3 records belongs to class yes, and rest of them belong to class no. So therefore we should go to the second part, that is the Tn records belongs to more than one class. Then we need to identify an attribute with the condition so that we can partition the record. So therefore there are 3 records here, as we can see, 3 attributes we can see, that is homeowner, marital status, and income. So we need to identify that any one of the attributes, and then we'll apply the test condition. So let's say if we identify the homeowner, so homeowner has 2 value, so therefore we will have the 2 outcome. Similarly, marital status has 3 value. We can go for 3 branches or we can go for 2 branches. Similarly, income has a continuous value. We'll see how we'll split. Okay. So up to this one, what we understood key for forming the decision tree, if we have the records and records belongs to multiple classes, then we need to identify one of the attributes and with test condition to partition the records into so let's say in multiple subsets. So now question is how to partition the records. Okay, and another question we need to address key, how to determine the split and how to determine which one is the best split. So splitting criteria indicate the splitting attribute with a split point, that is the test condition. So in split condition we will have the objective to get each partition as pure as possible. That means here is homogeneous. Homogeneous means most of the records should belong to a single class. So our objective of splitting should be that most of the record should belong to single class. if it is not, as you can see, the objective to each objective is to get each partition as pure as possible. Okay. So next, we are talking about how to get the test condition and how to split the records. So it depends on the attribute types. So there are nominal attributes, ordinal attributes, and continuous attributes. Nominal attributes, typical example of nominal attributes is, say, let's say color. So where we can say that whether the two colors are same or not, and we cannot say more than that. So let's say if I say the red color, so if there are other colors, so let's say yellow, so we can say the red is not, red and yellow are different and they are not same. But we cannot add red and yellow and we can get some results. Like if we add 2 plus 3, we will get 5. But in case of the nominal attribute, we cannot have that features. Next is ordinal attributes. Ordinal attribute is something where we can have the comparison and we can make them order, like CGPA. So if we can compare two CGPA, we cannot add, there is no meaning, it does not make any sense if you add the two CGPA, but we can make them in order. So that is something called ordinal attribute, and rest of the things are continuous attribute. Let's say age or time, those are everything as continuous attributes. So therefore, before splitting the attributes or before splitting the record, we need to find the attributes and then test condition. So attributes may have the multiple value. So which value we should take for splitting. So for that, actually, we should know that is whether this attribute is nominal, ordinal, or continuous. And another thing is whether we'll go for two-way split or we should go for multi-way split. As you can see that in previous example, like marital status has three types, three values. So it was married, and it was single, and it was divorce. So in that case, one can go for the three-way split or one can go for the two-way split. So splitting based on the continuous attributes, what we can do it, if it is continuous attributes like income, so we can go for the binary decision. So like income is less than 80K or income is greater than 80K, or we can form an ordinal attributes, or we can put them bucket, like say 70 to 80 income one bucket, then 80 to 90 one bucket, and then 90 to 100, and then 100 to 120. So that way also we can discretize the continuous attributes, and then we can partition the records. So now question is how to determine the base split. So as I said few minutes before that, so after splitting, we should get nodes such that many of the records should belong to single class. So more formally, that is nodes with homogeneous class distribution are preferred. So but how to define that whether the nodes are homogeneous or not? So we need to have a measures to find the node homogeneity. That means we need to find whether node is pure, and if it is pure, how much pure or impure. So that means we need to find something called the node impurity factor. So in the next slide, we'll be talking about how do you measure the impurity. So a metric is used for selecting the base split. So there are three popular metrics for finding whether a particular split will be accepted or not. As you just a quick reminder that main objective of partitioning the records is that we should get, after splitting, we should node should be homogeneous. Homogeneous means actually most of the records should belong to a single class. So therefore we have metric, that is three popular metrics for computing the impurity. One is Gini index, this is used in the CART. Another is entropy, and hardly it is used the classification error. Therefore we will focus on two, that is the Gini index and entropy. So here, say suppose we have a node where n0 number of objects belongs to class C1 and n1 number of objects belongs to class C1. Sorry, C0 and C1. So two class problem. And then n0 number of objects belongs to class C0 and n1 number of objects belongs to class C1. And there are two attributes. So there are two attributes. I think I can take this one. Yeah. So there are two attributes. One is attribute A and another is attribute B. Okay. So now if I use attribute A, so then we get a, let's say we have the original training data set. So we have n0 plus, as you can see, total number of object will be n0, n0 plus. It's difficult to write here. n0 plus n1, and then we got split. So we divided using the attribute A. So let's say we use the attribute A, and we got a split. So let's say subset here, and we got something here. And here also we have two classes, that is C0, C1. So here N10 and N02, this is correspond to this node. And M2, let's say this is correspond to here. Okay. And using the same initial, what is called is, let's say we can say this is the training data set. Using same training data set, but we use the attribute B for partitioning the records. So similarly, we get it same figure here. We got like this one, and then we have something like that. Okay. So here, this is, there will be a node here. We have node here. So now this is correspond to this part, and let's say this is correspond to this node here. Okay. So now what do we do it? We got this type of, now we need to identify whether it should be good to use the split A or attribute A or attribute B. So let's say we use same set attribute B. Okay. So basically we'll compute the gain. Gain means initially this was M0. Okay. So this was M0. That means actually this M0 correspond to this node, and similarly this M0 also correspond to this node. Okay. So if we go with attribute A, what is the gain? And if you go with attribute B, what will be the gain? So wherever we'll get the gain more than the other, so we'll use that attribute either A or B. So now question is, how do you compute this gain? So therefore, what do we do it? This node we compute the, as I said, the impurity or purity. What is the value of purity and what is the value of purity, and then we combine it. Similarly, we same thing we do for the attribute B. Okay, that we'll be discussing in the next. So here, so we use the Gini index to compute the impurity value in a particular node. Okay. So that is the formula here, that Gini at particular node, let's say this is T. Okay. So this is T, is defined as 1 minus summation over the classes PJT and then square. What is that PJT? PJT is the relative frequency of the class J at node T. That means if there are two classes, then we should do there will be two terms here. So let's say class 0 and class 1. So PJT means P class 0 at the node T. It indicates the how many records in this node T belongs to class 0, and similarly how many records belongs to class 1 divided by total number of okay, let me tell you here. Let's say here we have the class 10, say 10 records belongs to, so let's say this is class A, and 20 is here, and then this is, let's say, class B. Okay. So to compute impurity, what we have to do, we have to compute PJT. PJT means at the node T, and relative frequency for class A will be, say, 10 by 30. Okay, so it will be 10 by 30 and then square. Okay. Similarly, for other class, it will be 20 by 30 and then square. So I'll have an example in the next. So here, so Gini index for a given T is computed as I said here. So PGT is the relative frequency of the class J at node T. So now, what is the minimum value of this Gini T? When it will be the minimum value? So when this value will be 1. When this value will be 1? When let's say out of 30 sample, so all 30 sample belongs to class A. Okay. So then this will be 1 square 1. So this value will be 0. So that means node is pure. So therefore Gini value will be 0. Okay. So then when this value will be maximum? This value will be maximum when, so in earlier example, we had the 30 sample. So 15 sample belongs to class A, and then another 50 sample belongs to class B. So in that scenario, that, so this value will be maximum. I think, what is the minimum value here? So minimum value will be 0 and maximum value will be 1. So when it will be 1, so when this will be equally probable, all the classes are equally probable. So then I think I am wrong. Okay, I'll come here. We'll see one example. That is, what is the minimum value? Minimum value is this part. Minimum value is 0, and we'll see the when we'll get the maximum value. Maximum value will be I think next we'll see here. So let's say this example. Okay, so this example, how we can compute the Gini value. So Gini value is here 1 minus summation over PJT. So here value will be 6 by 6. So this will be 0. So Gini value will be here 0. So here what will be the Gini value? So Gini value will be 1. We can compute it 1 minus summation. Summation will have 2 terms. So one is 1 by 6. So 1 by 6, and then square plus minus is 5 by 6. 5 by 6 square. Okay. Okay. So next is here. So this is another example. So this is example. This value will be, I computed previously. This value will be 0.278. So this value will be 0, and this value will be, we can compute here 1 minus summation over, that is 3 by 6 means half. So this will be square. So, and it will be 2 times. So you multiply with 2. So it will be 0.5. Okay. So therefore, this value, when all classes are equally probable, that means number of samples are same across the classes. So we'll get the maximum value. So now question is, what we computed for individual node, what will be the Gini value. Now when we split it, so let's say we have splitted it like here earlier as we have seen it. So we splitted it. What will be the combined split? When a node P is splitted into k children. So in this example 2, so what will be the combined split? So combined splits mean we have to compute the individual impurity, and then we add it. That is something called weighted addition. So weighted summation. So weighted is how many samples are there. Okay, that proportion how many samples is coming in this branch. So that is n1 by n into multiplied with the split, what is called is the Gini at this node, and then we take the sum. So if it is multiple branch, then we do it. So that is something called the Gini at split. So as earlier example, we started with attribute A and then another attribute with B. So therefore, what we do it, we'll compute the Gini split at A and Gini split at B. And then what we do it, we compute the gain. Gain is nothing but after splitting what are the condition and before splitting what was the value. So that was M0, as if you remember a few minutes before, that is M0. So at that node we compute the Gini and what is the combined Gini value, and then we subtract it. Okay. So therefore this value will be close to 0. So therefore this value will be that subtraction will be positive. Okay. So now we move to the next. So computing Gini index, as we can see here, this is same thing. Yeah. So what will be the split for this scenario? So Gini split will be here 7. So 7 by 12 for this node. Actually one node is here, another node is N2. So in this example, what we do it here, 7 by 12 into Gini value of this part. So that is 0.40 plus 5 by 12 into Gini value of this part. Okay, so that is the Gini split. And what is the value at here? So it value is just few minutes before we have seen that each record, each class has six records. So then this value will be half. Now we need to compute. So what we see, what is the value, and then half minus this value will be the gain for so let's say attribute A. So in the similar line, actually for computing the impurity, so for our objective to find the impurity at particular node, there are another line is like one can use the entropy. So entropy for computing the impurity here. So entropy is like negative of summation of PJT. PJT remained the same, that is relative frequency. How many records belongs to class J at the node T, and then we will take log base 2 or PJT. Okay. So this also been used. So this is example of how to compute the entropy here. Yeah. So this is one example here, how to compute entropy in this example. Say negative of 1 by 6 into log 1 by 6 minus and so on. So we'll get the value 0.65. Okay. So similarly, we can compute entropy for this value. Okay. So 3 by 6 into log 3 by 6 minus 3 by 6 into log C. We will get log 3 by 6 means. So here this value will be how much? So this is log 3 plus log 3 by 6 means half. So it will be minus log 1. I think unable to plus log 2. Okay. So log 2. So this will give you the 1. So maximum value for two classes. So entropy will be 1.0. Okay. Otherwise, see if the all records belongs to same class, so this will be 0. Okay. So because log 1 will be 0. So similarly, in earlier case also we have computed the gain. So gain is like if you have a record, so let's say A, and then we want to split it, say let's say in multiple split. Okay, so then what we do it, what is the entropy at this point and what is the combined entropy. Okay, so in the similar line, combined entropy is something entropy of the individual node and then weighted by the number of records belongs to particular records in proportion. Okay, so if it is 100, so here is 10, so 10 by 100 into entropy of this, and then we have the summation. So that will give you the information gain. But information gain has a issue. It's like, say, if a particular attribute has many values, like roll number in a scenario that each student will have the individual roll number. So then if I go for 100 students, then if we go for the 100 split, so information gain will be the maximum, because for each split what will happen, this part will be 0 and then this will be the maximum gain. So to avoid this, what is done is there is something called I think we can see, yeah, gain ratio is used. So gain ratio is nothing but if there are multiple split, so that divided by the split info. So split info is something like that. So if, as I said, that 100, so 100 students, 100 split, in that case we'll get the value here. So it will be one, so let's say 1 by 100, so and it will be 100 times. So it will be like log of 100. Okay, so therefore, if number of split is more, this value will more, and this appear into the denominator. So therefore, this gain ratio also will reduce if there are 100 split. So this is also used for finding the best split. So now in summary, what you do it here, so let's say there are three measures I said. One is Gini, another is entropy, and another is the misclassification, which is hardly used. So that but definition is something 1 minus max j of pjt. So if in a class, so let's say in a node, if in this example earlier said 10 and 20, so maximum is 20 by 30. So then classification error will be 1 minus, so 20 by 30. So that is a classification error. So but classification error is not used. So these two parts are used for forming the decision tree. So in this example, so two class problem, this give is actually probability of a one class. So if it is 0.5, so entropy will be maximum. However, Gini will be half. Okay. And the misclassification again for one class, if it is 0.9, so therefore in other class it will be 0.1. So therefore we can see the different values here. Okay. So now is what we started from here. So let's say initial training data set, now we split it here. Okay, so because we are getting the much pure node here, so again we can split it here and so on. But when do you stop in splitting the records? See, stop expanding a node when all records belongs to the same class. So if you remember Hunt's algorithm first condition was something like that. If the all record belongs to one, so you stop it. So here is also that after repeated splitting, if we reach a particular node where the all records belongs to same class, then we should not again split that particular node, or stop expanding a node when all records will have the similar attributes value. So this is another criteria. Or what we can do, we can fix another threshold. If the gain is, let's say, is less than some value, so we stop it. Okay, so so that is the condition for stopping the decision tree splitting. So I think there are many things to talk about decision tree, but I need to stop here. So something it is inexpensive to construct, and extremely fast at classifying unknown record, because initially when I showed you on example here how to find the class level, and that class level, it is so fast because it is actually to identify whether a record belongs to a particular class. So it is just to trace the depth of the tree, and that will be a constant. So therefore identifying a class level is a of an unknown object is a constant time. Accuracy is comparable, so we are not claiming that accuracy is as good as, let's say, in today's deep learning technique, but it has many other advantage over today's techniques. So I think I don't have much time, so we'll stop here. Discussion stop over decision tree. Now we'll talk about something called Bayes rule or Bayes classifier. So if the relationship between the attribute set and the class is non-deterministic, in that case actually Bayes rule is used. So one example, as you can see, so doctor knows that if the patient has the meningitis, so there is a chance that patient will get the stiff neck 50% of the time. Okay. So we have more information. So irrespective of whether the patient has meningitis or stiff neck, so probability of any patient having the meningitis is 1 by 50,000. And similarly, another information we have in a particular region, let's say, so the stiff neck is 1 by 20. So using Bayesian rule, we can say in reverse way, if we have the stiff neck, what is the probability of that patient may get the meningitis? So this is this problem can be seen as a classification problem if you have the sufficient number of data. Okay, so for that we need to know a little bit about something called the conditional probability. Let's say A and C are two random variables. So random variables, it holds some values in the what is called is random variable. Basically it associated with some random event. Okay, and it will have some outcome. Let's say if we toss the coin, so outcome is actually head or tail. So similarly random variable here A and C will have some outcome. And what is conditional probability is that probability of a random variable will take a particular value given that the value of other random variable is known. So in other cases in previously, so having meningitis and stiff neck two are different issue. But if we know that the patient has meningitis, what is the probability that the stiff neck will be there? So therefore, this formulation is there. That is if the patient probability of A, where A is the random variable, given C, if we know that C has already been occur, what is the probability of occurring A can be written as joint probability of AC divided by probability of C. Similarly, if the probability of C given A could be written also, that is probability joint probability by and divided by probability of A. Now if you carefully see these two equations, so let's say if we replace this probability of AC from this equation, so this equation will be probability of A given C into probability of C. Now this is written in the next slide here. So probability of C given A is nothing but joint probability of A and C. Joint probability is nothing but from previous equation we can get the probability of A given C is multiplied by probability of C. Okay. So now we come to the point here what we promise ki if the patient has the stiff neck, what is the probability that he or she has meningitis? But previous information we had ki if the patient has meningitis, probability of if the meningitis is there for a particular patient, so what is the probability that he will have the stiff neck? Now this is the reverse case. Okay, so then what we can write, the probability of a patient will have the meningitis if he has the stiff neck. So therefore this is directly we got from this equation, that is something called Bayes theorem. And then we directly put the value, because this value already got it 0.5, And this probability is, we know that is independent of this joint probability is 1 by 50,000 and then this value. So then we'll get the 0.00 value for probability of having meningitis when the patient is already suffering from the stiff neck. So this information is, as I said, that can be used for classification problem also. So how to use this Bayes rule in classification? Let's say we have the two class problem. And what we have to do, as I said, the classification problem means we need to identify the class level of the unknown object. So let's say X is the unknown object. Unknown object means we'll have, obviously X will have a different features. So that is the features A1, A2 to AM. So what we do it, we'll directly say what is the probability that X may belong to class W1. And then this is the joint probability. From here we can write what is the probability that X, what will be the probability if X belongs to class W1. When it is known that X may belongs to class W1, what is the probability? And then we multiply the prior probability of W1 divided by Px. Similarly, we do the same thing for the other class. What is the probability that for a given unknown object X, what will be the probability that it will belong to other class? Okay. And then wherever it is maximum, so we'll assign to the class to the unknown object. So now if you carefully see both the equation, actually the denominator is having the same. So therefore we no need to bother about this part. Only we need to compute this part and this part. Okay. So what is that? Probability of X for each class W1 and W2, and then prior probability of each class. Okay. So this problem is actually, it is not very easy to compute this part. This might be easy to compute, but this is not very easy to compute. So therefore there is something called naive-Bayes classifier, where we assume that each features are independent. So then what will happen? So problem remains that what you do it, as I said a few minutes before, we need to compute this part. Okay. So this is more challenging because this will get from prior probability also will get from the data, but this is very challenging. So we simplify it. We assume that its features are independent. So to compute this part. Okay. So yeah, we need to compute this part. So as I said here, so computing this part is very easy. So like we need to estimate. So one estimation policy is the how many objects belongs to a particular class and divided by number of total training sample. So this is nothing but the probability, prior probability of particular class. Okay. So this is easy. Now to compute this one, we use the naive-Bayes. So naive-Bayes is something like that. Yeah, I think I am very close. So here, how to estimate the probability of X, that is unknown object, when class level is we assume that the class level is, let's say, C1 or C2. So this is, we can expand it, and then if we expand it, its features are independent. Then we can write the probability of the value of A1 given C1. We can multiply it here. Okay. And if it is a categorical attribute, computing this one is much easier. Okay. So what you do it, we compute that how many objects in the class C1 with the value A1 and divided by number of sample in C1. So that will give you this type of probability here, that what is the probability of A1, similarly probability of A2. Okay. So problem start if it is a continuous attributes. So in continuous attribute, we assume that say continuous attributes like in income, we assume that it follow the Gaussian distribution. Okay. So therefore, what you do it directly, we feed that equation. Let's say this is one example how to compute the what is called is the class level of an unknown object here. So let's say this is the problem here. And then we need to identify the class level. So what you do it, we have to find, I think we can show you maybe another 2-3 minutes. Yeah, what do we need to, we have to compute this part. Okay. Probability of X given class cell name. There are two classes. So first we compute the class no. So that is nothing but probability of refund, because this value is no, when the class level is no, in multiplied with probability of this value is merit when class level is no, into probability of income when it is 120. So now if you go back here, see the value 4 by 7, how you are getting for class level no. So I think we had, yeah, class level no, and then refund is no, right? Class level no. So this is 1, this is 2, this is 3, and this is 4. So therefore we get the value 4 by 7 here. So we get the value 4 by 7. Similarly here also merit, if we count, we'll get the value 4 by 7. And next we need to compute this value here, because this is a continuous attribute. Same thing we need to do if the we compute the probability of x, that is unknown sample, if class is yes. Okay, here we found key there is no guy that class is yes and with value merit. So therefore this value will be 0. We can check it, and then this value we need to compute. Okay, so this is already 0. Obviously the class level will be no. So here as we see that if it is we assume that if it is a continuous attribute, so we assume it is Gaussian distribution. So we compute the mean, sample mean 100 and so on. So we get this value and directly we put it here. And as this value is more than the 0, so then it class level is no. Okay. So I think Sir has already discussed how to evaluate the model. So we have to find something called confusion matrix. Using confusion matrix, one can find the what is called is the goodness of the classification technique. So this is something called a matrix where we have to row wise is like predicted class, what the algorithm says, and it is actual class. So it has a very good name actually, each of the entry. So here is something called the true positive. True positive means actually algorithm also consider as it is a positive class, and actually it is positive. So similarly, but this one as considered as a algorithm says it is a positive class, but unfortunately it is a negative class, is something called the false positive, true positive, and similarly false negative and true negative. So accuracy is very oftenly used for computing the class, goodness of the classification technique. So here accuracy is true positive plus true negative divided by this all combination here. But yes, accuracy has some drawback. Okay, so if the data is very imbalanced data, so one example is like if one class is having 9,990 points and other class only 10 points, so then if we have a classification algorithm which always says the positive class, still will get the accuracy is 99.9. So this is the problem with the accuracy. To address this issue, what if you do in the reverse way, if you consider this class is a positive class and this is negative class, so accuracy will be say 0.0001. So therefore this accuracy measure has a problem, and therefore what is done is like if it is totally very data is very skewed or imbalanced data, like what we find for the outlier detection technique. So in that case, what is done is, so best way to use the some other measures is something called precision and recall. Okay, so I think I am done. So I have taken too much time. So if you have anyone is having any doubt, I think I can address. Hello?
Yeah, hello, sir. Yes.
Yes.
Yeah, if anybody have any questions, please you can ask him now. It seems no questions, sir. So we will take a break for 5 minutes. Then shall we join?
Yes, yes, I think we should take a break and then
Yeah,
we'll
yeah,
join
yes.
at 8:05 or 8:10.
9-5. Okay,
Yeah.
9-5 we can join,
Oh,
sir.
it's a 9:05. Yeah.
Yes. Yeah. Okay.
Okay.
Yes, we can start, Professor.
Yes. Is my screen visible?
Yes.
Okay, so this part actually we'll be talking about clustering method. As I have seen that Professor Vishwanath was talking about unsupervised learning. So this is clustering is an unsupervised learning. So in this, we'll be talking about that is classification introduction, and then we'll be talking about introduction to clustering and details similarity measures, and then different clustering approaches. So just few minutes before I said that classifications will need to have the training data set, then we'll make the model, and then for unknown object we need to find the class level. So essential part for the classification technique is that we should have the training data set. But what happened for many scenario, we do not get the training data set. But we need to analyze the data. We need to know that what is happening. So in that scenario, we cannot use the supervised learning such as the classification technique, but we use unsupervised techniques where actually we do not need the training data set. Okay. So, and there are many unsupervised techniques, outlier detection, clustering, and many more. But in today's, we'll be talking about clustering. So here we go. That is, cluster analysis or clustering is to discover the natural grouping of a set of patterns, points, and objects. Let's say if one image is given to you, and then there are in the image we can see there are land, there are say water body, rivers, and other things. So automatically, if I ask you to find the what is called different region, so then one can easily say point out that this particular region is actually water body. So this particular region is a land, and so on. So that means actually one can find the natural grouping. So same thing is done by the cluster analysis by clustering technique. So we need to find the grouping of the objects. But problem is that natural grouping, how do you identify the natural grouping? Say one grouping, if this might be natural to me, but for someone else it may not be natural. And moreover, actually, natural grouping is not very concrete. It does not have very concrete definition. What does it mean by natural grouping? So therefore, the second definition of clustering is more accepted. It's something like that. So cluster analysis or clustering activity is to find group of objects or pattern we call the cluster in the data set in such a way that objects or pattern in a cluster are more similar to each other than pattern in the distinct cluster. It means it says that now we can forget about what is natural grouping. So now we'll find, if we have a set of objects, we should find a group. We group them in such a way that within a group we'll have more similar object than if you take the two objects from the two different groups, we'll have the less similarity. So therefore, we are introduced the term the similar. That means when do you say that one object is similar to other object? So we need to know how do you compute the similarity and so on. So there are other definition of clustering approach. Let's say we have a set of objects here, and then what do you want to? And then each object has a number of attributes. So, and a clustering is nothing but a partition of the objects here. So in such a way that each we have a subset C1, C2, and CK, and each partition here, each we say this is entirely is called the partition, but C1 is the subset of the data set in such a way that if we make the union of all these subsets, we'll get the original data set. And each clusters, each subset, no, there should not be any subset that which has not any elements, and intersection is null. And moreover, that if you take 2 points from the same class, same subset, that is we say the cluster or group of objects, will have more similar value than if the objects from the different clusters or different groups. So in summary, objective of clustering is that we should group the objects such that if you take any two arbitrary objects, if they belong to same class, will have more similarity, or say we should not use the term the class. So it is a group. If the two objects are from the same group, will have more similarity than if you take two objects from two different groups. So now there are many applications of clustering approach. Here biology, information retrieval, and so on. So now just few minutes before we talk about key, we should know that two objects from the same group will have more similarity than if you take the two objects from two different groups. So therefore we need to compute the similarity value between the objects. So similarity between a pair of objects, that is x and y, is nothing but a function where the domain is a pair of objects, and then codomain is actually it range from 0 to 1. And we are talking about the similarity value. If it is very close to 1, so then they are very close to each other, they are very similar to each other. Otherwise, that is, and if it is the 1 value, so then we are talking about, actually we are comparing the two objects are actually exactly the same. So there are different similarity measures. So very quickly I will be talking about only 2-3 similarity measures. So one is simple matching. So simple matching is nothing but, say, if we have a set of objects, if we have a two objects, and then object has only values 0 and 1, so then if they agree, that means if we have a objects to a pair of objects, and each vector has value either 0 and 1, so if they agree, if both are 0, then we'll consider as 1, otherwise we'll consider as a 0. So therefore, if both are 0, you'll get 1, and both of 1, if the both have the value 1, that also will be 1. So that therefore simple matching is like, we'll count how many times they agree. So if there are, say, let's 5 attributes, out of 5 attributes, say in three times they agree that both are 0 or both are 1, so then similarity simple matching will be 3/5. But problem is, if both are 0 also, then they are also considered as they agree. But both are 0, in very often actually we don't know the value. That is why it is 0. So therefore this has a problem. So we move to some other similarity measure which are actually used. So that is something called Jacquard similarity measures. So it was introduced late, I think in 19th century. So here, what is that? So wherever they agree means actually both value are 1. So in that case, we will consider that how many times both are saying key 1. So we can go straight forward. One example, that is SMC, that is simple matching. So that is 1 0 is mismatching, 0 1 mismatching. So 0 0. So this is 1, and another 1 1 and 1. So it is, that is why value is 2/5. In case of the Jacquard, we'll see how many times they agree on 1. So here 1 and here 1, and rest of the cases is they are not agreeing. So 0 we should exclude it. So therefore Jacquard similarity is 1/5. It should be 1/5. So here Jacquard could be used for finding the similarity between two sets, not only the vectors, even two sets. If there are two sets, that is A and B, so Jacquard similarity will be, so intersection divided by union, and then we should take the cardinality. So this is one similarity measure, that is something called Jacob. There are other similarity measures. So is called the cosine similarity. So cosine similarity is between two vector is like it find the angle between two vectors. So it is like x dot y. If the x and y are vector divided by individual value, we can go directly state one example. Let's say x is the value this one and y is this one. Then we can compute the dot product of x dot or x dot y. So it will be 3 into 2, 6, and then 0. If any one 0 means multiplication will be 0, and then 1 0. So another, I think you can see here 3 and 2, 6, and then individual value of the vector, so that we can compute, and then we can get the cosine value. So until now what we said is that is something called similarity or similarity value. There is something called dissimilarity value, which is opposite to the similarity value. In case of the similarity, we said is if it is very close to 1, okay, that means they are close to a maximum value is 1. So therefore, if two objects are very close, two objects, sorry, similarity value is close to maximum value, maximum is 1. So then we'll say those objects are very similar to each other. Here, Euclidean distance is opposite to the similarity value. That is why it is called dissimilarity value. Why? If the 2 points are very close, that means that value will be very less, but we'll say they are very similar to each other. So that is why it is opposite to Euclidean distance measures is opposite to the similarity measure. So that is why it is called the dissimilarity measure. As we know, the Euclidean distance formula is very simple here: square root of the summation of individual attributes value square. So as you can see in here, if we compute Euclidean distance, so 3 minus 2 square and so on. So Euclidean distance has a very good property. So that is something called metric property. So metric property is like a space is called metric space if you have a set of objects, that is the data set, and if you have a function, and function should follow this property. Function is like a pair of objects, and then it should be a real number including 0. Okay, so what is that? It should be, if you take any pair of objects, so distance always should be greater than 0, that value. And if it is the same object, so it should be 0. And distance, let's say here example Euclidean distance we are talking about, it should be symmetric. Symmetric means if you talk about any 2 points, so let's say from Benares to, let's say, Sri City, whatever the distance, and distance from Sri City to Benares, it will be the same thing. So that is something called symmetric property. And another one is the triangle inequality. Say distance from x to y plus distance from y to z is always greater than equal to distance from x to z. Okay, if we consider the 3 points, let's say Benares, Kolkata, and say let's say Sri City. So distance from here to Kolkata and Kolkata to Benares, here to Kolkata and Kolkata to Sri City will be always greater than equal to direct distance from here to Sri City. So this, if any function follow this property, we'll say that form the metric space, and we'll say it follow the metric property. So now we'll be talking about the clustering technique. So clustering technique is actually literature is very rich. It was introduced in 1958. Until many clustering algorithms are being introduced till date. And those clustering algorithm could be divided into two state division. We can do it. One is called the partitional clustering. Another is hierarchical clustering. So in partitional clustering, we'll get a single clustering. So in the examples, if we have a data set, so we can partition it into three what is called is cluster. So this is something called cluster. Here we have some points, here some points, and so on. So this all total we say is this is a clustering. Clustering is something a partition in mathematics. It is the same thing. So we can say is a division of the data following the earlier properties, that if you take the intersection, we'll get 0, and if you take the union, then we'll get the original data set. Another angle of another division of the clustering algorithm is which produce the multiple clustering. So here one example, suppose we have a data set, but we apply one clustering approach, but we get two partition. This is one partition, this is another partition. In this partition, we have two clusters, and here we have three clusters. Along with that, actually, if we carefully see, these two cluster is obtained from other one clusters here. Okay, so therefore there is a relation between two partitions. So this is subset of these clusters, and this is superset of this cluster. If these such relations exist, then we will say ki this is the outcome of one hierarchical cluster. One outcome of the hierarchical clustering. Okay, so this is one partitional clustering, this is another partitional clustering. So in summary, there are a class of algorithm which produce one clustering or one partition, and there are other class of algorithms which produce actually multiple partitional clustering. Okay, so there are few famous algorithm which very often use. One of them is the k-mean clustering approach. So in k-mean optimization, it optimizes the sum of the squared error. Sum of the square error is defined as follows. So if there are k clusters, so within a cluster, what we do, we compute the distance. We compute the distance from the arbitrary point in the clusters to the centroid of the cluster. Centroid of the cluster is something we define key. If we have a set of points, and then we take the mean of those points, so that is something called the centroid. Okay, so we find the distance from centroid to the all other points, and we sum them. So that is something called the squared because of the error. So it is something called this is something called error, and then we take the square, and then we need to minimize it. So how it works? So we have the simple algorithm here. See, what do you do it? First, you take the k points as the initial centroid. Okay, and then we have a two-step. We repeat it. Form k clusters by assigning each point to the closest centroid, and recompute the centroid for each cluster, and then we keep on doing this part. So we have two steps. First is we need to form the clusters, and then how do we form the clusters? We'll form the cluster by assigning the points to the closest centroid, and then we recompute the centroid, and we keep on doing until two successive iteration we get the centroid. There is no change of the centroid. I think one simple example here we can see. Let's say we have a data set here 2, 4, 10, and this is a single dimensional data set. We are not talking about multi-dimensional data set. So 2, 4, 10, and we need to find the partition using k-mean clustering, and we assume that k-mean, k stand for the number of clusters. So therefore we assume that k equal to 2. Okay, so first step, if you see, first point is select k point as the initial centroid. So therefore from this set of points we need to find any two arbitrary points. So let's say in this example we find 2 and 4 are the arbitrary points, and they are the initial centroid. Okay, so initial centroids and 2 and 4. So next step is we as you see that we need to find the cluster. We need to form the cluster. How do we form the clusters? We assign the rest of the we assign the points to the closest centroid. So therefore what do we have to do? We have to find the distance from 2 to 2 and 2 to 4. Obviously 2 to 2 distance is 0. So therefore this 2 will be the closest. Similarly, what we do it, 4 will find 4 to 2, and 4 to 4 is 0, and 4 to 2 is 2. So this 2 and 4 will be two different cluster. So 10 to 2 is distance more with compared to 10 to 4. So therefore, what we do it, we need to form the clusters. So now this is the clusters. So there are 0.3. So 3 will be in the cluster C1, and C2 will have the points. Please note that distance from 3 to 2 is also 1, 3 to 4 is also 1. So we have arbitrarily we choose any one of the cluster. So therefore we get a cluster C1 and cluster C2. using the L2 distance, that is Euclidean distance. So what is the next step? If you carefully, again we move back, sorry. So we need to recompute 2 steps. First is forming the clusters and recompute. So we please note it. So we form the clusters. Now what we do it? We recompute the centroid. Centroid means we take the mean. So it is a one-dimensional point. So you take the mean. So 2, 3. So mean will be 2.5. So we recompute it. And here also, if you add it, so 4 plus 10, so 14 plus 12, 26, and 20 plus 30. So if you add it, so you will get, and then divided by number of points. So you will get actually, yeah, you will get 1 and 2, and then you will get the mean 16. So or recompute the centroid. Next, what is that? Now this is the present centroid. Now we need to form the clusters. 2 steps. We have to form the cluster and recompute the centroid. So we keep on doing until there is no change in the centroid. So in initial centroid was 2, 4. Now centroid changed. So therefore we have to, now centroid is 2.5 and 16. Okay. So therefore we go to the next step. So we assign the point, we find the distance from 2 to 2.5, 2 to 16. Obviously 2 will be close, 4 will be more closer than 16, and then 3 will be more closer than 16. So now 10 to 16 is 6, and 10 to 2.5. So therefore 10 also will come to the this cluster. So now this is the formation of the next iteration. We form the cluster 2, 3, 4, and C2 will be 10, 12, and above all points. Okay. So once we get the cluster net, what is the step? Now we recompute the centroid. So we find the average 2 plus 3, 5 plus 4 divided by 3. So 3.0, and this will be mean 18. So next step, again, once we get the centroid, next we need to form the cluster. How do we form the clusters? It is the same thing, that we compute the distance from 2 to 3, 4 to 4, 4 to 3, 4 to 18. Similarly, the points which are close will be close. The points closest to the centroid will form a clusters. So therefore, the C1 will 2, 3, 4, 10, and C2 will be these points, and then we need to again recompute the centroid. So after recomputation, we will get the 4.75 and 19.6. So again we assign the points, and then we will get the point 2, 3, 7, 4, and something like that, and then there is change of the centroid. So again we need to compute the we computed the centroid, and then again we need to form. Okay. So now if you carefully see it, there is no change of the sorry. So there is no change. Yeah. So there is no change of what is called centroid and also cluster. So then here we'll stop it. So that is all about the k-mean clustering. So k-mean clustering is for anything. If you wish to see how it works if you intend to use the clustering approach, so easiest way to apply the k-mean clustering if the data are numeric. Okay, so time complexity is linear, so that is the number of iteration into, for each time number of iteration, and each time, so we need to number of data set, number of data points, and then we have to compute the distance from the each point to the cluster. So that is kn. So that is why time complexity is I into k into n, and I is actually is very number of iteration. So after 5, 6, 7 iteration, it get converged. So therefore we say k into n. Kn is very small. So many times we say that is that it is a linear time clustering approach. Okay. So, but it has many drawbacks also. It cannot detect outlier. Obviously, this is the clustering approach. But another main drawback is it can find only the convex shape cluster. If there is a spherical kind of shape in a data set, then it is good to use. It is applicable to only numeric data. This is another drawback, that because every time we need to compute the centroid means we need to compute the mean. So therefore, it should be numeric. You cannot work with non-numeric data. Okay, and with different initial points, it produces different clustering approaches. Okay. So like we have a data set, clustering could be even, so this will form a clusters and this will be divided into two. Okay, so this is one example. I think I will stop with this clustering. I think I will get another 5-7 minutes. Okay, so it is not recent. In 2000, there is one clustering approach. One clustering approach was introduced, used called the bisecting k-mean. And it happens that bisecting k-mean it is found that bisecting k-mean is better than the k-mean clustering approach. So idea is very simple. What do you do it? We apply the k-mean clustering where k is 2, okay, and we do the many times, okay. So let's say k-mean we apply first, okay, with k is equal to 2, okay. So then we will get 2 clusters. So among between these 2 cluster, what we do, we'll choose any one cluster. Again, we apply k-mean. Okay. So and we apply k-mean many times. So not only that, say let me tell you in more formal way. Let's say initially we have the data set here. Okay. So then what do you do it? We bisect the cluster using k-mean and a number of times. So that means if you have a data set here. I think, yeah, I can take this one. Let's say we have a data set here, okay, initial data set. Now what do you do it? Remove a cluster from the list. So we have taken this point as a first cluster. Entire data is itself a cluster. Then what do you do? We apply k-mean clustering with k equal to 2. So therefore we get it, let's say like, I think we have a place. Yeah. Sorry. So then we'll get 2 clusters here. This is one cluster. So let's say we get one cluster here, one cluster here. So this is apply k-mean one time. Another time we apply, we'll get another cluster here, another cluster here. Same data set like initial. So similarly, we'll get here and we'll get here. Okay. So now what do you do it? We compute the SSE value. What is the SSE value for this partition? What is the SSE value this partition? What is the SSE value for this partition? So let's say we apply 10 times. Then we'll get 10 SSE value. And we'll choose one partition. That means we'll choose this one if it has the least SSE value. And these 2 cluster we put in the list. That means initially it was 1. We have taken it, so it was 0. So now we have 2 clusters. Now among these 2 clusters, we choose any one of them and again do the same thing. That means if you take this point, again we have a 1 cluster and we'll have a 2 clusters one time. Another, again we do it here. Okay. So again we do it here. And then we compute the SSE value here. We compute the SSE value here. So wherever there is minimum, we choose these 2. Again we push back. Earlier it was 1. Now we are putting it. So this become 2. So this become 3. So now if the at the end of the day, if we want the number of cluster is 3, so we stop it here. Otherwise, if we want number of cluster is 5, so then again we do the same thing. And it found that this gives much better result than k-mean clustering, because one thing is we are doing many things and every time we are finding the at which situation we can get the SSE value. I think, yeah. So k-mean could be seen as a optimization problem because we have finding the SSE value. So I think, yeah. So this is one simple mathematics here. So what is that? We have to minimize the SSE value. So for minimization, what we have to do? We have to take the derivative, partial derivative, and we set to 0. Objective 2, actually within a clusters, the points from where we will get the least SSE value, that is we need to find. So then it could be shown that this is nothing but the centroid points. So if we get only the centroid point, then only we'll get the least SSE value. That is the objective of this part. Okay. So as I said, that hierarchical clustering approach is find the multiple clustering. Okay, so there are 2 approach for hierarchical clustering. So one can go for, so let's say finding initially big cluster and you divided it and then you go to you'll get a required number of clusters. Otherwise, you start from the say individual points and progressively you merge the points. Okay, this is the two approach we say. So for this one, what we need to do it, we need to find the distance matrix first step. And then what you do is merge the two closures. There are two ways. One is, as I said, the bottom up approach, that is agglomerative approach, and then progressively we merge. I think time is not permitting. So there are three ways that we compute the distance between two clusters. I think one example we can see here. Yeah. So as I said, that single linkage is a agglomerative approach. So first is there are 5 points. So 3 and 5, we merge them. 3, 5 distance is 0.7. And then we see the 0.14 is also closest, next closest. So we merge them. And next we merge here. And then finally we'll get the one big cluster where the all points are there. So this is one example of the single linkage. And then actually hierarchical clustering, most of the hierarchical clustering approach, but nowadays also density based hierarchical clustering approach also we see. But traditional hierarchical clustering approach are distance based approach, but it has many drawbacks. So now state of the art clustering approach is actually density based clustering approach. It can find the arbitrary safe clusters. It does not need to provide the number of cluster required in beforehand. So therefore, this approach is more very frequently used nowadays. So one approach is DB-scan, even though it is old, but there are many variant of DB-scan. So and recent also work hierarchy, no need to find the threshold. DB-scan needs some threshold value, but automatically one can find the threshold and find the clusters. Okay. So I think I stop here. So if you have doubt, maybe I can take questions.
Thank you, sir. So if anybody have doubt, you can ask him now. Okay, I guess there are no questions, sir. Thank you very much. Thank you for like a clear explanation of base classifier first and decision trees, and now, okay, this clustering techniques. Thank you very much, sir. Thank you very much for
Okay.
the session.
Okay, sir. Thank you. Thank you. Good night, sir.
Yeah, good
Madam.
night, sir. Yeah, good night. Thank you, everyone. Thank you for all.